Good evening, everybody. My name's Matthew Connell. I'm a senior curator here at the museum. I'd like to start by acknowledging the Gadigal people as the traditional custodians of the land on which we stand, and pay my respects to elders past and present of the Eora Nation. I'd also like to extend that respect and welcome any other Indigenous people who are here tonight. Welcome to the 2014 Einstein lecture. I think it might be the second last event of the 2014 Ultimo Science Festival. The Einstein lecture has been running now for 9 years, presented by the Australian Institute of Physics and the Powerhouse Museum. And on behalf of the museum, I'd like to say thanks to the Australian Institute of Physics for bringing this opportunity to us again. They have a wonderful Einstein lecture in store tonight, but before I ask Secretary Fred Osmond to introduce our speaker, I'd like to draw your attention to the little survey forms that you were given as you came in. If you wouldn't mind filling those out, the data that we collect from those is what helps us get our funding for next year's event. So if you could please do that, that would be terrific. So do enjoy your evening, and now I'd like to ask Fred Osmond from the Australian Institute of Physics to come and introduce our 2014 Einstein lecturer. Fred?
Ladies and gentlemen, boys and girls, welcome to the Powerhouse Museum and welcome to the 9th year of the Einstein Lecture. Each year, the Australian Institute of Physics, New South Wales branch nominates a distinguished speaker whose work has covered a wide range of topics with an emphasis to Einstein's ideas and their consequence of physics and technology today. The Einstein Lecture is held each year and is presented by the Australian Institute of New South Wales and the Powerhouse Museum as part of the Ultimo Science Festival 2014. We are very fortunate to have our distinguished speaker tonight, Associate Professor Orsola De Marco. Orsola De Marco, a PhD, Associate Professor and future Fellow, Department of Physics, Astronomy, Macquarie University, is an astronomer whose research work was on stellar evolution and binary interactions. Born in Italy, Orsola studied in London at University College and worked in Zurich at the same institution that Einstein studied and worked. We are very fortunate to have Orsola as our distinguished speaker tonight, as she will reveal the fascinating world of astrophysics from her personal experience. May I present the speaker for the 2014 Einstein Lecture, Associate Professor Orsola De Marco, on the entitled talk, Pocket Astrophysics, Everything You Need to Know About the Universe to Negotiate Your Everyday on Earth. Please make her feel welcome.
Hello. So let me get over with the technical stuff first. Let's hope it works as it did before. Yes. Okay. It's really great to be here. I just gave this talk earlier on to a group of high school students. It's a bit strange to repeat it so shortly afterwards, but I'll do my best. So I wanted to start with a connection with Einstein. My talk is not really about Einstein or its work, but I have a strong connection with Einstein. This is a bit of my home, and you see him there, right? Hold on, this is buzzing now. Here they are. That picture I bought when I was 13 years old, and I was a teenager, and I didn't like people very much, and I was crying a lot. And there it is. I did a little project on the special theory of relativity, and I bought that, and that was on my bedside table for a long time, and now it's down at the bottom shelf somewhere. My second brush with Einstein happened in 2005 when I was at the American Museum of Natural History. And 2005 was the centenary of the great 3 papers that made Einstein famous, one of which got him the Nobel Prize. And an exhibit was put together because of that. And I had to write this essays in connection to a teacher's course. And here is one of the promo for that essay. And on that occasion, I got my very own Einstein action figure, which is mine. You all want it, I know it. But my talk will not be about Einstein. It'll be about how to make astrophysics, such a remote, faraway thing, matter to you tonight in your everyday life and tomorrow and thereon. I have a little picture here that I found from the internet, like everything else, of course. And there's 3 ladies here, and they're commenting on the comet, and they're saying, comets, everybody knows they're really, really dangerous. They bring bad luck. And in fact, last night, Madame Gauchy died. And I love this because it's really, I mean, we all know that is rubbish, right? But there's many, many things today that we still think and believe because of hearsay or because everybody thinks so. And of course, as soon as there's one thing that fits our belief, we use it as evidence. Just the fact that one person died means nothing. Of course, it's not statistical. So tonight I will talk about misconceptions and things of this nature as well as other things. So here is a very, very skimpy outline. I will tell you a little bit about an astrophysicist and what they do and how they get there. I will talk about a few relevant things, things that matter, and also a bunch of things that really don't matter. I mean, people think about horoscopes and it's rubbish, right? Doesn't matter. I'll talk a little bit about the search for meaning that we all do, not just astronomers, and a little bit at the end about my work, which is very impractical, completely doesn't matter to anybody, but it's fun. So how do you get to astrophysics? I have this stick at the end of my face that is a bit irritating, sorry. Well, you start by asking why, okay? There's kids here in the audience. You guys are the best. You ask why. And there's teachers in the audience, I'm sure, and parents. Don't stop them, right? And actually, don't even answer the question. Turn it around. Make them realize that this is really one of the most important activities and that there isn't always a good answer. And yeah, it's the search for the answer that matters. So here's the stereotype police is going to come and get me. But do you need to be geeky? These are geeky kids. Or do you need to be cool to become an astrophysicist? Well, it doesn't really matter, right? All it matters is that it's you. And that you're happy within what you are. But what does matter is that you really constantly wonder why and ponder and think, this guy just said that. Doesn't make any sense. Don't drink it. Just think it. So another thing that matters, of course, again, more stereotypes here, is that we love science. Of course, if you want to be a scientist, you have to love science. And in fact, that you have passion and curiosity. And for those of you who think, well, I like a lot of different things, and I don't really know where my passion is, well, find it. Go find it. Because that passion can drive you through problems, which invariably happen in anybody's paths and careers. Now, personally, my path through astrophysics is a geographic one, as most of my colleagues is. I started off in Italy. I was born in actually Padova, not Bologna, but I grew up in Bologna. It's really beautiful. It's a wonderful city. And I did a high school there. And then after that, through some more complications, I actually ended up in London, where I was at University College to do both my undergraduate degree, similar to here, 3 years, and then after that I followed on and did my PhD because I was still very convinced I wanted to be a scientist. And after that, what do you do? Now you're super qualified, maybe overqualified, and what job can you do? So I really wanted to stay in academia. I wanted to be an astronomer for life. You can also go into industry and do all sorts of other things with a degree and a PhD in physics or astronomy, or indeed any other science. I wanted to stay in astronomy, so I took a fellowship where I would do only research in Zurich, in Switzerland. And that's where I actually brushed in with Einstein again. I was at the Eidgenössische Technische Hochschule, I can't say it anymore. This is a picture from the 1800s, and Einstein was there for 4 years doing his actually teaching diploma, amongst many other things he did. And after that, I returned to London briefly for another fellowship, and then I moved on, enough of the rain, and I moved on to New York City. And I moved to the American Museum of Natural History, Hayden's Planetarium, which became a very important place in my life, and the story will continue about the Hayden in a moment. After about a decade at the Hayden, I decided I really wanted to teach undergraduates, as well as do research. And so I looked for a teaching position, and I got one at Macquarie Uni, where I am today, and I've been for 5 years. You have to go behind the map to go to Australia. So what do we really do? Okay, now I've done all these things. I've been a fellow. I've been at the American Museum of Natural History. So what do we really do on our day-to-day life? Just like all of you, we sit behind a desk. So this is Sébastien Lepine, who was a colleague at the American Museum of Natural History. And he looks for nearby stars. He's trying to get a census of the nearby stars. And you think, well, that must be easy. They're nearby, right? They're bright. But actually, it turns out it's really hard to distinguish them from the further away stars that are brighter. And what he would do, he would compare plates taken 50 years apart and see anything that moves. And of course, as our common sense tells us, if something is moving with a certain speed in front of us, it'll move more if they're close than if they're far away, relatively speaking. And every time he found one star that moved, he would put it on his wall. Eventually, there was no more room, and he was gone. So another thing we do, aside from sitting at desks, is go to telescopes. Not all astronomers do. Some are theorists. But I have done quite a bit on my day. This is the Canada-France-Hawaii telescope on Mauna Kea in Hawaii. Beautiful place. But sometimes people say, are you sure you're going to work? I say, yes, it's just that telescopes have to be on high mountains, possibly on islands, because the prevailing winds don't bring dust. You're above a lot of the weather, and they're really usually beautiful places. Here's another one, a Kitt Peak National Observatory. I was on a ridge where other telescopes were, and this is the 4-meter. And of course, telescope observing today is not the fantastic and romantic notion that we had from old days when you look through a telescope. You're in a room like this. Today, the screens are a bit flatter, but other than that, it's the same. This is a telescope operator. Should I comment that he's sleeping? And with feet on, it's not really looking proper, is it? But the telescope operator moves the telescope. This was a relatively big telescope. It's a 3.6-meter wind telescope. And they moved the telescope. And in my case, I don't have a good reputation with, I've broken a couple of things. And so he would tell me, you go sit there, don't move, and don't touch anything. And so I had my computer where the observations would come through, and that would be all I did. And he would move the telescope and do the rest. We go to conferences, of course. It's not just about creating knowledge, it's about sharing knowledge, not just with undergraduates, but with each other. So this is a conference in 2010 in the UK. And of course, I put here a much more distinguished conference. I should really not make this comparison, but it's a bit embarrassing. This is with Solvay meeting in 1927, the pictures being colored. Half of the people in there have a constant named after them. I can't say the same for these ones. Another thing we do, we have regular lives, right? So this picture is, some of you will recognize one person from the pictures in the audience. You have kids, so you have lives, you have normal lives, but you also have other kids, right? Here there's both types of kids. These are my biological kids, and these are my mind kids. These are my first 3 PhD students, and Dimitri is here today. So what else do we do as astrophysicists? Well, here is a bunch of things that come to mind. We definitely spoil the fun for cute little kids, and this is one of my favorite cute little kids, Drew Barrymore, who's still around, much older now. Why am I saying that? Because of the famous adventure of Pluto. Who doesn't know about Pluto today and what it went through? But we're going back now a few years. Now, Pluto, the 9th planet, dare I say, well, at this point of the story, it's still the 9th planet, was discovered by Clyde Tombaugh in 1930. And it was named by this little girl, Venetia Burney. She was the 11-year-old granddaughter of the librarian of the Oxford Bodleian Library. And he was kind of a man in high places. He had friends. He talked to the guys at Flagstaff, Arizona. And within a very little time, the planet was named. Now, Pluto the dog, amazingly, appeared for the first time in 1930 also, but later on in the year. And actually, I was looking to see whether Pluto was named after the planet, and Disney people don't remember exactly how the name came to be. Now, we don't have much knowledge of Pluto. This is the best image we have today. They're taken from the Hubble Space Telescope. As you can see, they're quite murky. The difference is just that Pluto rotates, so you can see at different phases. And here was a 2005 picture from the Hubble Space Telescope, having discovered Nixon Hydra just then. So we know very little. There's actually a mission today, the New Horizons, that's going to get there end of next year, beginning of the year after. So we should know a lot more soon. In fact, we'll have images as good as we have of, say, Jupiter. It's going to be quite exciting. But what about Pluto? Well, in 2001, in January, I was at the American Museum of Natural History when this article appeared. Pluto's not a planet only in New York. As she walked past the display of photos of planets at the Rose Center for Earth and Space, Pamela Curtis of Atlanta scrounged her brow, perplexed. There didn't seem to be enough planets. She started counting on her fingers, trying to remember the mnemonic her son had learned in school 8 years ago. My very educated mother just served us 9 pizzas. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. I had to go through the whole thing to figure out which one was missing. She said, Pluto. Pluto was not there. Now, I wanted to show you, I have this little cutting. This is from the New York Times. I lived there, and I remember, this was the first page of the New York Times in January that year. And I thought, oh my God, really? And in fact, I went to the museum where I was working, and I realized, yeah, there's no Pluto. Now, let me show you. This is the Hayden Planetarium, and in the exhibits is compared to the sun. And here are the 4 giant planets to scale, and on the railing down there you can't see, there are the 4 terrestrial planets, and Pluto's not there. So why not? Well, the fault of this not being put there was this man's, Neil Tyson's. So Neil had looked, when he basically designed all the exhibits, so the Hayden Planetarium had opened in 2000, so just a year before. When he designed the exhibit, he went through the literature and realized there actually is a controversy over what Pluto really is. And what this means is we don't really know when it was formed, how it was it formed together with the other planets or before or after. And so because of the controversy, he took a side. He decided, well, I think Pluto's not a planet. Perhaps it is a Kuiper belt object, one of these sort of pebbly stuff that's out in the outer solar system. After that, well, let me just tell you a bit more about this, and then I'll tell you what happened after this New York Times article. So we know today there is this Kuiper belt. It's just like a belt of pebbles and snowballs, effectively. And today, after that article came out, we actually know a lot more. In fact, we even know of this one object called Eris, which is more massive than Pluto itself. So there are stuff like Pluto out there, and maybe, you know, if we started calling everything a planet, this would be a planet too. What happened after that article was this. There was so much noise and so many phone calls and so much press and hate mail from 6-year-olds, and I'm not kidding. I was looking on the internet for something, and I found this one, and I had in my hands things just like this. Dear Mr. Tyson, I think Pluto is a planet. Why do you think Pluto is no longer a planet? I do not like your answer. Pluto is my favorite planet. You are going to have to take all the books away. Your friend Emerson York. Now I shared an office with the person who was opening these letters, by the way. So there was quite a lot. Now, interesting of this letter, I mean, this kid can be excused. He's clearly very young. But what about liking an answer? You shouldn't like it or dislike an answer in science. You just get it, and the next day try to disprove it. That's what we do. And books are old by the time they go to press. So fine, take all the books away. So what did the Pluto story teach us? Well, it taught us that you should never trust science books, first of all. The trust is really not a word that should compute in physics or astronomy or science. And that science is asking questions to which there isn't a right answer. There's just a right or answer, right? The next day, you'll always try to better what you did the day before. So Pluto taught this really great lesson in a very simple way, a way that could really be understood by 6-year-olds. And that is phenomenal, I think. He's also taught something else. I mean, he taught so many things. He taught that classification is the mother of science. When you don't know how something happens, you just take it, you classify, and you make lots of categories. You realize one is more populous than the other, and then you start to interpret. So it is important to understand whether Pluto is or isn't a planet, because by doing so, you then make the next step in understanding how the origin of the solar system was. I actually learned today that the director of the International Astronomical Union, which is the big body that oversees all astronomy, at the time, in 2006, when Pluto eventually got demoted to not being a planet, he's actually right there. So don't take it up with me. he's right there. So what else? What else? Well, here we go. We are Harbinger of Doom. This is a bust of Cassandra, who used to predict all these nefarious things and be hated for it. Why am I saying this? Because, well, I'm telling you now, we have these things. This is an artist's rendition of what happens in the end moments of a massive star life. So it collapses, it rotates a lot, and it seems like perhaps some of them eject a very beamy, so very collimated beam of radiation, very hard radiation, gamma rays, and they do that. Okay, so that's great. Who cares, right? There's not that many of these things, and they're far away. However, one day, this guy, Peter Tuttle, is my oldest friend in Australia, and he is a professor at Sydney Uni. And he's done this really great technique with, this is the secondary mirror of the Keck, and he's invented this technique with some colleagues that can see really small things far away. And he took a picture of this, and what this is, actually he has a movie of this, and I don't have it, and it goes around and around. There's 2 stars in there that rotate around one another with about 10, 20, 30-day periods. And as it does so, it sprinkles a dust lane that goes around, and if you fit this pattern, it's an exact Archimedes spiral. And what that tells you is that this thing, the plane of the orbit, is exactly 90 degrees to the line of sight. So The two stars in there are going to go supernova sooner or later, sooner perhaps rather than later. And if the pole of these stars is aligned with the orbit, which is likely, well, they're going to beam us. Now, how far is it? Not far enough. So what happens? Well, there's actually a few papers out there that try and talk about what if we get a beam of gamma rays directed to us from less than 3 kiloparsec, something that should happen every twice in a billion years. Well, it turns out that it would set up a chain reaction in the upper atmosphere that would result eventually in the depletion of the ozone layer. And so that's a lot of UV radiation now coming from the sun, and that's not good. So it possibly happened once before at the 450 million years ago extinction. And certainly there's consistency with the data there, but we don't know for sure, of course. So another thing, I've told you that we could be fried by WR104. Next thing, or maybe even before that, we can get hit, right? So this is the Arizona crater, about 50,000 years old, about a mile across. It's really pretty new in geological time, so it's beautiful. It's not been eroded. There's no trees, so you can see very well. Of course, the moon bears witness to a lot of cratering, a lot of impacts, many of which happened a long time ago when there were a lot more debris around. But these things happen even recently, to 50,000 years ago. Now, of course, we all recognize all these figures, right? So this is Shoemaker-Levy 9. It was a comet. It passed by Jupiter, got disrupted into pieces, and these pieces hit Jupiter the second pass, and these are the scars, right, on the planet. Things like that do fall, and they will hurt if you fall on your head, but the probability of that is very low. And of course, there's things like this. This is Tunguska in 1908, something that would have been about hundreds of meters, tens to hundreds of meters in diameter, explode about 10 to 15 kilometers above this remote place in Siberia and flatten 2,000 square miles, or square kilometers of forest. Nobody died because nobody lived there, but there is some eyewitness accounts. That was something that exploded with about 1,000 Hiroshimas worth, about 10 megaton of power. And the shock waves what flattened the trees. Today, with this anti-ballistic checks, we know that there's something that explodes with about 20 kiloton of every year in the upper atmosphere somewhere. So this thing is about a once in 300-year event. If this had happened over London, it would, of course, not have been good. But of course, if it happens somewhere else where there's nobody, it's okay, because it doesn't have repercussions elsewhere. Now, we all know about the dinosaurs' demise. This was at the Cretaceous-Palinogene boundary, 66 or so million years ago. They retrieved the crater, which is actually very difficult to find. It's not an obvious one it's been found with particular techniques. A Chicxulub, which was concomitant with that extinction and possibly the cause of it. That was so big, was kilometer size, that it would have had a lot of repercussions also on the other side of the planet, not just where it fell. So what about these meteorites? Do they come? How often? Well, here are the odds. 500 meteorites reach the surface each year. Okay? So these are things that will hit, but they will not make much of an impact unless you're under it with your head. 50 to 10 meters once per year, they burn up or explode. So this is like the one that happened in Russia last year, and they came in, and in fact, the damage was the sound wave, the shock wave, that broke a lot of glass, and a lot of people got hurt because of the glass. Bigger, like Tunguska, once every 5,000 years. Again, not much damage unless they hit something like a city. 1 to 2 kilometers, a few times every 1 million years. This would cause climate change everywhere, not just where they hit, because of the dust that's thrown up, and it would obfuscate the sun for a period of time. Anything bigger than that, 50 kilometers, 10 to 50 kilometers, is much rarer, of course, but it would cause mass extinction, possibly completely globally, and there is nothing we can do and hide. Interestingly, at the museum where I was, American Museum of Natural History, the provost was a paleontologist, and he was completely against the idea that meteorite impact caused the extinction of the dinosaurs, because there's still a lot of questions about the fact that little animals, like animals with 50 kilograms or lower body weight, didn't actually go extinct. And it's not really clear exactly why. And so here I want another demonstration. Science is not just the way it is. Oh yeah, 66 million years ago, something hits, the dinosaurs go. Science just is still wondering about that. So what is the lesson? The talk of lesson from the asteroid impacts. So upon discovering something flying, people look at the orbit, like they take a few pictures over a few days and calculate an orbit. And then they calculate whether or not it'll hit Earth. Now, these calculations are not precise to the millimeter or even to the kilometer. In fact, with initial data, you just have a family of orbits, and it might hit Earth. So they say, well, it'll hit Earth of January 1st, 2029, with a probability of 3%. Of course, the probability is something that most people just don't relate much to, so the newspaper will say, oh, January 1st, 2029, that's it. Now, this is exactly what happened for this asteroid called Apophis. Apophis is still out there, fortunately for us, it's not hit us yet. There was a calculation, just like I said, that it would hit in 2029 with a 3% chance. After a few more measurements of the orbit, they realized that it wasn't going to hit after all. There was a small chance that it would hit the keyhole, which is a particular area of space where if it does go through, it'll come back in 2036. But after a few more calculations and refinement of the orbit, the error bar went down, and Apophis was fine, and it was not going to hit us. And of course, the newspapers will now say, aha, the scientists were wrong. But we're wrong, of course we're wrong. What is not right or wrong is about the fact that you always refine your answer. And I still hear people say there's a big conspiracy theory of this or that nature. Scientists fight all the time. What conspiracy? We never agree on anything. And that's actually the nature of science and why it's so great, that you're constantly trying to better each other. It's a self-correcting system. So what if we do find something that's going to hit us in 10, 5, or 1 year? What do we do? So I asked the audience at one was school kids, so I asked them, so I had all sorts of really great theories. And the two I will report are, one person said the obvious. Oh, we're going to shoot it, right? We're going to shoot it with a big bomb. And another kid said, we better get out of here. And I'll come back to that because that was a really good comment. So we have, if you shoot it, it's just going to, we might break it up. But the energy of even a big atomic bomb is nothing compared to the kinetic energy these things have, right? If you break it up, as Neil Tyson said, well, now you have to evacuate 2 cities instead of 1. You take one of these. This is my, I love ET. This is, you take a spaceship and you park it close to the asteroid. Hopefully you have had time to get the spaceship ready and launch it and go there. And you park it nearby, and then you use your boosters to move it away. And what is the force that between the asteroid and the spaceship? Well, it's gravity, right? So this is called a gravitational attractor. Now, of course, we don't have the technology to do that, particularly in a short time, but this is a good method. There's a few others, but very fantastious. Anyway, let's move to misconceptions. Why do I have a toilet? Because I, too, thought that in the southern hemisphere, the water goes down the hole in the other way from the northern hemisphere. And, of course, it's not true, and you can test that yourself. Just go home, fill the sink, and you can make it go down both ways by just stirring it a little, right? The reason hurricanes and the other ones, cyclones, typhoons, go in opposite direction is because on big scales, if indeed the rotation of Earth will do that. Now, first misconception. I actually prepared this talk in a different form a while ago, and it was before 2012, so this had more oomph. So there was the movie 2012, which was about the end of the world. And the reason for the date was that apparently in the Mayan calendar is this idea that the cyclic eras ending, one of them ends in 2012. Apparently, I was looking it up. They're not even agreeing. No, the historians and Mayan scholars don't even agree on that. But anyway, this thing was caught by the press and, of course, by the internet and blown into, yes, we're going to all die in 2012. Now, I'm not going to tell you anything anymore about this because I have a wonderful clip by Neil Tyson, which he actually gave me permission to use tonight, about that, and he just is great. So here we go.
TV, the world is thinking.
Okay, The Planets Today is a marvelous work of fiction. Oh, yes. Yes, there is no such thing as Planet Nimburu or whatever they say. It's just fiction. And they cite sources that cite NASA sources. They don't cite NASA. Check the websites, you'll see. And it's all related to the doomsday predictions of the year 2012. Yes, that's what you're getting at. That's behind your question, isn't it? Yes. 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 You want to know if the world is going to end on December 21st, 2012. Because the same website that tells you about Planet X, this secret planet that has a strongly elliptical orbit that will come into our zone in 2012 and knock Earth off its axis, combined with, on December 21st, 2012, that the center of the galaxy, the sun and the Earth will come into perfect alignment, and the excess gravity will then also tip Earth off its axis, and it'll be end of the world as we know it. This is what these web pages will tell you. Turns out, if you go to December 21st and look at the star charts, it's true. the center of the galaxy, the sun and the earth, will come into perfect alignment. It will. It's true. It's true. What the site does not tell you is that that happens every year on December 21st. They left that out of the account. So it's a fun work of fiction. Earth will be here before, during, and after 2012. I will add that the movie 2012 that's being marketed right now, that's going to come out in 2012, and they want you to do all the homework for the movie. So they say, just Google it. And if you Google 2012, it's filled with thousands of web pages on Doomsday, written by people who didn't take enough science in school. So you Google it. I saw some of the previews for it, and I was worried that we would, all of us in this business would just be inundated with having to sort of correct misconceptions. And then I saw what they actually show in the movie. And the movie's like, aliens come, and they take over the Capitol. And I said, oh, that's just another sort of, like the movie Independence Day. And that's fine. It's just Hollywood.
Okay, so you said it all. Moving on. The moon, does that have an effect on us? I was interviewed at a radio station in the southern United States with actually a big group of people listening. It was several million. It was really a big deal. And all they really wanted from me was the scientist stamp of approval that indeed the moon and other things that they were talking about is acting on us, on our behavior, because of gravity. Now, I'm not an expert on the effects of light, and so we know that the moon has things with crops, and there are other interesting effects that are perhaps worthwhile. But gravity? So they say, well, because the tides, right? If the moon can influence the oceans, and our head is made of water, a lot of water, right? So why not? Well, it turns out that the force of gravity on our head is very, 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 I should say that as many zeros as very weak indeed. The force of a pillow near your head at night is 1 trillion times stronger. So do we worry about the effects of pillows on our behavior? And also another thing I pointed out was that that the moon, the high tide is spring tides, if you will, are new moon and full moon and new moon. So the same force is when the moon is full as when it is new, so completely not there. And of course, at this point, particularly people who want the stamp of approval on pseudoscience, they just don't listen anymore. They put the phone down or whatever. Next, on my miscellaneous misconceptions is the horoscope. There's, of course, you might know that the horoscope is just the constellations that are lined up on the ecliptic. So every moment on Earth, if you look at the sun will be in front of a given constellation. There's not just 12. Depends how you divide. A constellation is just a patch of sky. It's an area, right, that has a boundary, which is completely arbitrary and defined by us. It's even changed over the decades. And so there is actually a fucus between Sagittarius and Scorpius, and there's also another one I forget the name of that dips into Pisces. But that's not really the point. The point is that you can cut it any way you want. Lots and lots of people identify themselves in a given horoscope of a given day. But if you take a given horoscope and read it in front of a room full of people and ask whether people identify themselves, there's never any correlation with the sign, their sign. And there's lots of other ways in which you can test this and show people that doesn't work. What about UFOs? Everybody asks a scientist or an astronomer about UFOs. Well, there's a lot of interesting things out there. Some, like bolids, are beautiful. They're actually shooting stars effectively, maybe a little bit bigger than the grain of rice that constitutes most shooting stars, maybe like a pebble. Many have color, depending on what they're made of. Copper will give you a green hue. They're completely explained. They're not UFOs. Sometimes they move extremely slowly, and actually I've seen one myself when I was in New York and I was living on the 10th floor, and I had a good view, and it moved really weird, or at least I felt it was weird, but it was totally a bolide. Other things are not fully explained, like earthquake lights. There's lots of different types of earthquake light. People have lots of theories to explain exactly how they are lit up before an earthquake. It's not really clear we understand very well. Just because it's not explained doesn't mean it's aliens. And of course, there's things that have been dismissed, like crop circles, which are beautiful. But they were, the early ones were actually eventually revealed to be the masterpieces of these two guys who had shown that when they did it, how they did it, took pictures while they did it. And of course, there were a lot of copycats as well in all sorts of interesting designs. But what about real UFOs? What about the real search and desire to understand whether there is somebody out there? So this is a picture. It was hailed as the first picture of an extrasolar planet, and it turned out that this might be a planet, a fat planet, or maybe a small star. But anyway, today we know, thanks to Kepler, thousands of planets. The first one was discovered in 1995 by a technique called the wobble, if you will, and it's really seen the star wobble because of the unseen planet orbiting around it. That technique discovered a lot of really fat type Jupiter-like planets near their stars, like Mercury would be near the sun. But later on, Kepler found actually a lot of super-Earths. These are more massive versions of Earth, and some of them are in the habitable zone, which is the zone near a star where liquid water is possible. So, hey, this is pretty cool. I mean, this has happened. This was during my PhD. It's happened pretty quickly. Can you imagine what we will know in like 20 years? We'll start really characterizing the atmospheres of some of these planets. So this is really amazing. That's where really the energy should be. Does life exist elsewhere? Has it been discovered before? There was a big controversy a while ago about this meteorite from Mars that was found on Earth. And this meteorite are these formations. There's lots of different ones that look like bacteria on Earth. These are not organic. This is just rock. They're fossils, effectively. And there was a huge controversy because of lots and lots of papers saying, yes, it is, or no, it isn't. And today it's decided that based on this alone, we can't really tell whether this is just rock or whether there was some kind of Martian life. Mars in 2000, well, when I went to the museum, about 2002, was discovered to have subterranean water, liquid water. Okay, I bet there's something there. And I bet we'll know soon because we're going back to Mars. With the next mission will be a sample return mission. And the next one, perhaps a manned mission. Well, we'll see about that if the space program revives. So another place that would be a good place to look, except a lot more expensive than Mars, is Europa. Europa is one of the moons of Jupiter. It is a thick, it's an ice ball in the sense that it has a crust of ice, 20 kilometers thick, with an ocean underneath. And these are cracks on the ice, and the brown is stuff that seems to seep through. And the color indicates that it might well be organic material. That doesn't mean life, it just means organic chemistry. But warm water usually has life. So we might not be able to go there and dig. It might be a bit too expensive and maybe not very easy to do. But Mars would be, I think, the next bet. So what about life? I told you about Europa, perhaps Mars. What type of life would we expect there? Slime mold, little things, bacteria. What about more complex life, animals, maybe even intelligent life? I read this book a while ago that I really, really enjoyed by this a geologist and an astronomer. And they wrote a book about all the things that happened to Earth that made it possible for life to develop, enough time for life to develop. And it turns out there were a lot of weird things that happened to Earth, all of which are rare, including being hit by Mars-like body that created the moon, that stabilized a spin axis so that we don't topple like some of the other planets do. And that, of course, keeps the season steady. And that's really important. So they basically put forward the idea that life, slime mold, probably everywhere. Complex life, probably very rare. Who knows? I had, for a long time, the SETI on my computer, you know, on the screensaver. If you don't look, you'll never know, so it's fun. So what about, well, the space program. Now, there's a lot of debate on whether the space program should be halted, whether it's too expensive, whether we should care about life on Earth before we think about space. However, there's a lot of good arguments to pro the space program. It's not that expensive. The space program in the US costs $7 billion. We spend $10 billion a month in Iraq. Putting in perspective, it's not because one is war and one is not. It's not even that. It's just it's not that much money. It's a few pennies per person per day. And in fact, you could double that amount of money and have the greatest space program and really start thinking about Mars. Humans on Mars, this is an artist's rendition of terraforming. It's not even about that. It's also just continuing the exploration that we started. It is unquantifiable to what extent the space program has helped produce engineers, scientists that went on and did biology and medicine and all other things. You can quantify some of the great discoveries that came from the space programs in terms of technology, but that's nothing. That's nothing compared to the way the kids started getting excited about science. I certainly was one of them. I was not alive on the moon landing, but I still get goosebumps every time I think of it or every time I see it on a movie. And this is Atlantis, but when which one was the last? I now forget. I'm getting a senior moment. But the last space shuttle to come back was in 2009. I just arrived in Australia, and I had my son watch it, hoping that he'd remember the last dribble of this incredible machine. And of course, now we don't have that anymore. And of course, we are exploration. We've always done that. How can you stop it? We need to go where we haven't been before. And of course, this "before we can" comes from Mallory, right? Why climb Everest? Because it's there. So astronomy, practical, yeah, tells you a lot of things that can happen, that maybe they happen rarely, but they do happen. And also about interesting debate and how science works. I always advocate astronomy for teachers in particular because it's a good marketing for science in general. It is something that you can use as a hook to teach any kind of science, and indeed even philosophy. You know, astronomers do think about, you know, the search for life itself. Is, you know, are we alone? It's a hugely important question in our being. But let's shift gear, and enough with useful stuff. Let's talk about really useless astronomy, which is the type I do. So I work on old stars. I also am a really huge movie fan, so I particularly, he's my favorite actor of all times. Actually, this is more my type of old star. So this is Sirius, the brightest star in the sky, visible even from the southern hemisphere. And this is Sirius B, which is a white dwarf, and it was relatively recently imaged because it's so close to Sirius being such a bright, glary star that it was really hard to image. It is a white dwarf. The two stars are kind of approximately the same mass, give or take a factor or two. And this star has become really small because stars live a long time, they expand during their life as they get older, and eventually they lose a lot of mass and shrivel down to this white dwarf. This is for stars like the sun, or about up to 10 times the mass of the sun. Now, I'm particularly into couples. So as I like old stars, that makes me an old couples therapist. And so this is, of course, a human couple, and this is a star couple. When two stars are close to each other enough, and particularly when one of the two expands during its evolution, they can interact. And this interaction, it's fantastic. It's like fireworks, right? You can have lots of interesting light phenomena, variability, explosions, jets, you name it. But more importantly, these stars will never be the same after this interaction. They really alter each other's life. So I wonder, sometimes you look at a star out there and you think it's single. And you try and interpret what you see based on a star that's lived its life alone. But maybe it has a companion that you can't quite see. And so that star is today the result of its companion. It's like taking, if you're a shrink, and you take a person you're trying to analyze, and then you realize they'd be married and had a really kind of happy marriage or terrible marriage for 50 years. You will see that person in a very different light. And that's what I really am into right now in my research. I really want to know to what extent stars are the way they are because they've been interacted with by companion stars or maybe even by their planetary system. We're learning that there's so many planets out there. So this is one of the things I study are nebulae. And this is a nice little kind of portrait of lots of different nebulae. There's different types of stars in here. But the type of nebula I'm interested in are those that display interesting patterns. And I've been wondering, together with others, why these patterns? Where do they come from? And I'm particularly interested in patterns like this being created by the interaction with a companion. So how do I study this? Well, we try to find binary stars in the middle of interesting pattern nebulae. But I also work on simulations. So this is actually an artist's rendition I'm about to show you that lasts about a minute, that shows how two stars might interact to make an interesting nebula that could have a bipolar shape. So this is a star that's becoming big, is growing in its evolution, and this is its companion. As it grows, the outer layers will be attracted by the gravitational force of the companion, form an accretion disk, and in this particular picture, the companion gets completely swallowed up by the giant star. And inside, it gives energy, it's called orbital energy, to the envelope, and the envelope might acquire a axisymmetric shape. In this case, it's like a UFO type shape. When the star loses more mass, that mass will encounter this equatorial enhancement of mass, and in this case, create some kind of bipolar nebula. Now this is an artist's rendition. This is somebody who has the software, and I'm telling him this, and he makes a nice picture. But what I'm about to show you in the next and last slide is actually an actual simulation. Simulations are a lot more complicated. You're trying to get the physics right. You're trying to put gravity in it, and radiation, and magnetic fields, and what have you. And every simulation will have a different cocktail of physics that you think is relevant and important in a given physical situation. So here you have your giant star. The dot in the middle corresponds to its core, which is a really compact little nugget about the size of Earth. So these stars are really big, like 3-4 astronomical units in size, and their cores can be as little as Earth. And this is its companion. And it's in an elliptic orbit, and what it's going to do is going to go like this and just go around. Now, where am I? There you go. And so mass, again, gets attracted to the other guy, and the orbit is altered enough that at the next pass, they'll start merging. And here, the companion and the core of the giant dance around one another, giving so much energy to the envelope that it gets kind of lifted away. And so this is just one of the modern, recent simulations that Jan, one of my postdocs, has been carrying out. And we're trying to understand what comes of that. What is the end product? What light do we get from it? Do you get jets? Do we get nebulae? So this is really it for me. So I've been telling you about what astrophysicists do, how we get there. We definitely are fun spoilers. And that's because we tell everybody it's all about the debate, guys. And the debate has to happen all the time, in all fields of life. We also guard against the dangers of space. Of course, we don't guard, because just like everybody else will be under the meteorite when it comes. We're pedantic, guard against misconception. I know some of you guys might enjoy the horoscope. It's fun sometimes. You read, oh, look, today I'm going to have such a great day. Fantastic. It is fun. But, you know, it is just that. It's fun. We search for meanings together with everybody else, about planets, about life elsewhere. Where are we going? If you think about cosmology, I'm not a cosmologist, but they're really thinking about, is the universe going to accelerate into what? And what was it born? And what happened before that? And we do look for inspirations, just like everybody, and we hope to pass on that inspiration to our students and our friends and our colleagues and inspire others. And of course, many of them do absolutely useless stuff, like myself, but that's fun too. And hopefully I can inspire with that as well. And with that, that's it for me.
Thank you very much, Orsola. We have time for some questions, and I'm going to put you on the spot a little bit because we'll take one question for each planet in the solar system. So how many questions does that make? Okay, any questions? Yes, down here.
It always takes a moment. Yeah.
Fantastic, Orsola. I just want to ask you something that you said very early on, one of your slides. You said, trust no one in science. That was one of the little bullet points. And I'm just wondering, doesn't science hinge on trust? Don't we trust scientists that they don't make up the data and just get the answers that they want? Doesn't trust a key facet of the scientific process?
But isn't that wonderful that you're using the word trust in that way? Yes, we do trust others, right? And that's because it's a fundamental human quality. But it's in the realm of psychology in that sense. So yes, of course, I am, I don't know, I might be driving a bus, so I have to trust scientists because I'm not going to do that myself. But in truth, I'm not trusting them. I am trusting the process, right? I trust that the process is self-correcting. So in that sense, yes, the word is valid.
Another question, towards the back there.
This actually very much relates to the last question. How much, okay, science tends to contradict itself. I remember reading Stephen Hawking's, and he was basically disproving Einstein. Now, how accurate do you think science is, and how accurate do you think our science is? Because I remember reading, although we've had thousands of years of chemistry and medicine and stuff like that, about 15 years ago, they discovered Bohr's model of the atom was all wrong.
Yeah.
But chemistry works. So how accurate do you think our science is at the moment?
It's really a good question. And if you think about it, I mean, Newtonian mechanics works really well, right? Really, really well, except for a few things, like the precession of the orbit of Mercury and other things like that. So why doesn't it work there? And this was actually troubling scientists at the turn of the century. And that was that, among other things, is what pushed people to think beyond the thing that worked. So you asked how good is science right now? Well, it's kind of good enough. I mean, it's not, no, I shouldn't say good enough because we want to go beyond, but it is in the sense that a lot of the predictions made by science allow us to create tools such as lasers, right, that are very, very useful. So in that sense, it's good enough. But it is very true that paradigm shifts have come in history. And again, at that same time, around the turn of the century, there were these ideas that we kind of had everything worked out, except for a couple of things that maybe will just get worked out tomorrow. But in fact, those couple of things turned out to be huge problems with the current paradigm and brought about the next paradigm, which of course was from Newtonian mechanics going on to relativity. So who knows when the next one is going to happen, right? And what shape will it take? Of course, there's so much stuff that is really profoundly not understood. I mean, in astronomy, take dark matter. Let's forget about dark energy. We're not even there yet. Dark matter. Dark matter, so it totally exists. I mean, the galaxies wouldn't rotate like that if there wasn't enough matter to keep the rotation curve that way. Except, does it interact with light? I mean, what is it? So there's lots of ideas out there, but maybe they're wrong. Maybe there's something really different that we haven't figured out. And of course, let's go on to dark energy, which is another interesting. So who knows when the next thing is going to come, and who knows how big it'll be? Will it? But the reassuring part is whatever we have, including, say, Newtonian mechanics before the big paradigm shift of the early 1900s, it works well. It works okay. It does a lot of good things that we can still use it for. And in fact, in my astronomy, I don't use relativity. I use Newtonian mechanics because I'm not in a regime where we're very fast, so it does well for me. My things going around, I'm following that with Kepler's laws, right?
Yes, one here.
Have you discovered any old star couples or found them?
Yes. So one of the things I do, so I do a little bit of theory and a little bit of observation. So that just means what it is, right? So I go to telescopes and I work with people looking for things, but I also use the computer to try and figure out whether we can figure out a model for the things that I and others have found. So we do look for binaries, for old star couples, in the middle of this pretty nebula that I showed, because one idea is that when they're that pretty, it means there's two. And sometimes we find them. Sometimes it's really hard because sometimes, so you have this white dwarf. White dwarfs can be very, very dim, but my type of white dwarf is before they get really dim, so it's actually quite bright. And the companion could be, imagine the sun, but cut the mass by half, right? So it's a half solar mass, and they're really, really dim. And these objects, there's not many in the universe, not many in the galaxy, so they tend to be far away. So these little dim stars, they just disappear. Sometimes you can find them by the same way that we find extrasolar planets, by the effect of their gravity on the star that you do see. Sometimes we're lucky and we can image it and it's kind of far enough and the object's close enough that you actually can see too. But yeah, so we found a bunch of them and we follow them up, try to characterize their masses, their brightness, their period if we can find it, and then connect that to the nebula to see whether the nebula makes sense as a result of that interaction that might have happened.
Thank you. Hi. Do you have more than one in a couple? And if there is more than one, what's the reaction with each other?
More than one meaning three?
More than one star, yes. 3, 4, 5.
Four, yeah, lots. If you think about solar type stars, so not my guys, not my old guys, the young guys, right? And you look around and you find sun-like stars. About 50% are in binaries, and of that, 10% are in triples. And then there's also quadruples and quintuples and other hierarchical. And so sometimes during the life of the system, it'll become dynamically unstable. So the orbit will, either one star will go in or one will be ejected out. In globular clusters, which are this hundreds of thousands to a million stars together, they're kind of fluffy clusters that in orbit around our galaxy. Those environments are quite dense. There's a lot of stars per whatever cubic parsec. And those interact also with other stars that are not in the binary, but they come close enough that if there is a binary, it gets completely broken apart. So there's a lot of instability, and then a lot of instability through the interaction that I have described. But the triples are interesting. So every time with a binary we can't figure out what's going on, we say, it's a triple. There must have been another one there, that now it's not there anymore. So scapegoat of people who work on binary stars is the triples.
Yes, one over this side.
That's right, I can still. Oh yeah. Do binary stars, when they form, do they form next to one another, or do they form separately and then kind of get caught up in one another's gravity?
They form next to one another. But you hit an interesting point in astronomy. So there's a lot of things that are really, really unknown in astronomy that we can't figure out. One of them, star formation. So star formation, we all understand the generics, right? Okay, there's a dust and gas cloud, it collapses under gravity. But beyond that, the understanding of exactly how many stars do you form and why do you form stars like the size of the sun as opposed to more often much, much more massive? Do stars form in different ways in different environments? Did they form differently in the old days? Old days meaning of the universe. Well, we know now, we're starting to zero in the idea that the first stars were really massive, like hundreds of solar masses, and that formed not necessarily in galaxies, but really early on. So we really don't know. But the idea is that you get a bunch of stars forming from one cloud, so they're all quite close, and that two or more of them will be bound in each other's gravity. But a very interesting side question of this is that, we kind of know that planets form in a disk. So there's the cloud collapses, you get the star in the middle, you get a disk around, and it cools, and you get the planets. So why not forming a binary like that? Why not forming the sun in the middle, and then one of the planets actually is massive enough that starts ignition of nuclear fusion itself? So we don't know, right? Brown dwarfs, which are these weird objects jammed between planets and stars, they're less massive than stars but more massive than planets, and they burn deuterium. Do they form like planets or do they form like stars? So there's really a lot of very big open questions, even in such a relatively simple to understand field.
We might just take two more, if that's all right.
Hi, I'd just like to ask your opinion on the theory that our sun was once part of a binary system. If you did any work on that, or knew anyone that did any work on that?
I remember, actually, I'm not entirely sure, but I remember when I was at the museum, one of the people who was working there was actually claiming that if there was still today a companion to the sun, put it at some distance, put it at, I don't know, Pluto's 40 AU, put it, I don't know, a few hundred AU, maybe a bit more than that even, maybe 1,000 AU away. It wouldn't move very fast. It'd be pretty dim. It could be very dim. Let's say it's a brown dwarf. So it could be there. We just don't know about it. So today, since those days when Mike said that, the surveys have really increased in depth and breadth. So I wonder whether it's starting to exclude that today there is currently a companion to the sun. There could have been one before, and then it was ejected. We know now, because we know of a lot more planetary system than we did even 2 years ago, we know that there's all kind of combinations. There's planets around binaries, so the binary stars each with planets. There's planets around a binary system. There are binaries where one has planets, one doesn't seem to. So there's all kinds of combinations. And that's because the birthing environment is very complex, and of course the formation process is very complex. So it's possible.
Okay, last question just there, gentleman. Yeah.
Over the last 200 years, we've had an enormous number of very learned and household name scientists that have come up with the most profoundly important, I am told, say, numerical constants that to us ordinary human beings are so infinitesimally tiny that you couldn't even imagine them, but they've invented them, discovered them, when they didn't have measuring instruments and whatever. Today, we don't seem to have those sort of people. We hear very little of this, say, the important building blocks of physics and science. Is there a reason for that?
We were just talking about this afternoon, and I was looking at that picture with the Solvay conference where half of the people that were Planck, Dirac, Madame Curie. I mean, it was amazing. And then my conference, I mean, I shouldn't really put myself down like that. But anyway, you're right. You're totally right. So I wondered, what was it? Was it a fluke that all these brilliant people were born approximately at the same time? I think that sometimes things happen that we call enabling technologies, and that doesn't have to be a technology. It can be also a bunch of discoveries that either trigger a wave of inspiration in the people who are already there, or maybe if it isn't truly an enabling technology, take when the Sloan Digital Sky Survey appeared, suddenly a lot of discoveries were made just because nobody could have done it before because the technology to get these really big swaths of survey sky were not there. So I think perhaps in those days there was an enabling technology in the form of the Lorentz experiments. There was of course the Michelson experiments. There was a whole bunch of things that happened more or less at the same time that were truly inspirational and very revealing. And maybe the men and women at the time around caught on to that. And so there was a whole bunch of brilliant people that could express their brilliance. So by this token, I think there's probably a lot of brilliant people, or probably recognized already, but maybe even more brilliant if they had that experiment made, or maybe that tool that they don't have right now. I don't know, this is just one idea.
Thank you very much for those questions, and we'll have to move on, unfortunately. I've been looking at, I've had plenty of time to look at your action
Hands
figure
off.
up here.
That's
if I was going to steal it, I wouldn't have brought any attention to it, but he's looking very grumpy.
He has a chalk in his hand, I love that.
Oh, okay. Oh yes, he does, right. Okay, let's get on. Thank you very much for that wonderful talk. Ladies and gentlemen, what have we learned about astrophysicists tonight? Well, we've learned that they can be geeky or cool, or in Orsula's case, maybe geeky and cool. We've learned that they enjoy spoiling kids' fun. We can often find them in Hawaii with their feet up, disagreeing with each other, but really twiddling their thumbs and waiting for the first flight to Mars. They're definitely obsessed with the end of the world. They're harbingers of doom. And if we didn't have enough to worry about, there's now WR104 out there waiting to beam a killer ray of X-rays. Or is it just a ploy to scare the general public so we keep funding them to find them? I don't know. She doesn't believe in astrology, but Pisceans always say that, don't they? But I think finally what we've learnt is astrophysicists can be incredibly inspirational, passionate, articulate, engaging, and finally they can deliver absolutely brilliant Einstein lectures. Thank you very much for your talk tonight. My name's Scott Martin. I'm with the Australian Institute of Physics, and on behalf of the AIP, I'd like to thoroughly thank the Powerhouse Museum for their support and use of facilities yet again in this 9th year. It's a very, very popular event in our calendar. So in particular, I'd like to thank Matthew Connell, Frankie Lee, Tilly Berlin, Ian Wolfe for preparing an excellent media release and broadcasts, the Science Teachers Association of Australia, the Royal Society of New South Wales, and of course you, the audience, for being here tonight. The New South Wales branch of the Australian Institute of Physics does have a range of events for the general public, and some of these you will have seen flyers for outside. For example, later in the year in November, we have the very popular Women in Physics lecture series. On the 18th of November, we'll have a very interesting talk on Aboriginal astrophysics over 40,000 years. And on the 6th of November, we're hosting the Physics of the Mind event. And the other thing to talk about is the postgraduate day, again on the 18th of November. But check our website out, and we're also on Meetup and Twitter and Facebook. Did I mention that already? I did, yes, we're there too. So thank you very much, everyone, for being here tonight. That concludes the proceedings, and I hope you have a safe trip home. Thank you very much.